Hello, I'm Benjamin Rigsby, and this video will cover a literature review I did on the fracture mechanics of skin. So to start off with, we need to look at the structure of skin. Skin has three layers: the epidermis, the dermis, and the hypodermis. For the purpose of this video, I'll be focusing on the dermis because it provides most of the elastic strength and fracture toughness of skin. Within the dermis, there are two primary proteins we're concerned with: collagen and elastin. You can see those in the figure on the screen. One important thing to note about collagen is demonstrated in the stress-strain response. As you can see in the figure, collagen starts out in phase 1 bunched up and tightly compacted. As strain is applied and gets larger, collagen starts to unravel and straighten out. By the third phase, it's completely straight and the stiffness of skin increases dramatically. One other important thing to note about the behavior of collagen, that it stretches and increases stiffness with stretch, is that in our everyday lives this is important because we want to be able to move freely. And if skin was a very stiff linear response material, it would impede our movement, so we would spend a lot of extra energy just moving around and doing everyday tasks. Moving on to the fracture toughness of skin. Skin is a complicated material. It's not a rigid body. And so, since we're used to working with rigid bodies in solid mechanics and in fracture mechanics, we have to approach this problem differently. We have to simplify the problem. Here you can see that a sharp interaction point is being used. And in this case, that physically means that the researchers were inserting a needle into skin. What that does is it reduces the plastic zone of deformation to a very small area around the needle point. It's a sharp interaction point. And so that makes the plastic component negligible. Notice that there are three components of work that are equal to the work done by the needle. There is the work to fracture, the change in strain energy, and the work done by friction. The last two, the work done by friction and change in strain energy, are reversible components of work, while the work to fracture is irreversible. So using this idea, researchers will insert the needle into the same puncture wound in the skin a second time. The second time gives only the reversible components of the work. And so subtracting the two equations will give you fracture toughness in terms of only measured variables: the force to insert the needle, the depth which the needle was inserted, and the crack area. Finally, I want to show what researchers have demonstrated with crack propagation in skin. So if you look in the figure, you can see that the skin was started with an edge notch, put in a tensile tester, and started pulling it apart. And this is a traditional test done on many different types of materials to observe crack propagation. As the skin is stretched, the crack opens, but as it opens, the crack tip begins to blunt. The reason that it blunts is because the collagen fibrils, which I talked about at the beginning of the video, begin to stretch and bend and shift and reorient, and the result is that the crack tip blunts and the radius of curvature at the crack tip increases, so that the stress concentration decreases, and the authors did not observe fracture at all. The skin did not fail by fracture. And that's pretty interesting because that behavior is unique to skin. And the authors pointed at collagen's ability to reorient as the thing that gives skin this unique property, that it has such a high fracture toughness that it can actually stop crack propagation in this case. Thank you for watching.